Welcome to the NESC Academy unit on wavelet synthesis. In this unit, we will be synthesizing a series of wavelets in order to satisfy a shock response spectrum. And typically this would be used for a shaker shock test, although there are also other uses for wavelets that we will cover in upcoming units. This unit also contains some MATLAB exercises, so you may pause or stop this presentation at any time in order to complete the exercises. This unit is sponsored by the NASA Engineering and Safety Center, NESC Academy, and by Dynamic Concepts Incorporated of Huntsville, Alabama. My name is Tom Irvine, and I am the instructor for this unit, and you're welcome to send me an email or give me a phone call if you have any comments or questions. Thank you. So in this unit we will be synthesizing a series of wavelets in order to satisfy a shock response spectrum specification. Now each individual wavelet has a property such that its net velocity is zero and its net displacement is zero, and that is also true for a summation of wavelets. On the other hand, if we were to use damped sinusoids, we would need a compensation pulse in order to achieve zero net velocity and zero net displacement. But in this unit we're focusing on wavelets. Now the vibration control computer itself should have its own algorithm for generating a series of wavelets for an SRS specification, but we're going to come up with a MATLAB script in this unit which should be able to outperform the vibration control computer in terms of synthesizing a waveform which also minimizes the displacement and minimizes the acceleration. And these are two key limit parameters in terms of shaker shock testing. Here's the equation for an individual wavelet. The acceleration amplitude is represented by W sub m, and that's equal to A sub m, where A is the acceleration for wavelet m, and then we have two sinusoidal functions. And the argument of the first sinusoidal function is 2 pi f sub m over n sub m. Now f sub m is the frequency of the wavelet, n sub m is the number of half sines, and this must be an odd integer greater than or equal to 3. Then also in the argument we have the time t minus a delay time represented by t sub dm. For the second sine function, we have 2 pi f sub m, and then we have our time argument again. So this is the equation for an individual wavelet, and we're going to have a series of these wavelets for acceleration-based input pulse in order to satisfy the shock response spectrum specification. Here is an acceleration time history. The y-axis is acceleration in g, and the x-axis is the time in seconds. And this is a typical wavelet waveform. So the frequency is 74.6 Hertz. There are 9 half-sine pulses, and the delay is equal to 12 milliseconds. So then on the plot you can see 1, 2, 3, 4, 5, 6, 7, 8, 9 marking the individual half-sine pulses. So what we essentially have is a sine function where the amplitude is modulated by another sine function. Here is a typical shock response spectrum which can usually be performed on a shaker table. This comes from Mill Standard 810E, method 516.4, crash hazard for ground equipment. And the same specification should also be in the more recent revisions of Mill Standard 810. This is a shock response spectrum. The amplification factor is Q is equal to 10. The left column in the table is natural frequency in Hertz, and the right column is the peak acceleration in G. Now the first coordinate pair is 10 Hertz and 9.4 G, and as it turns out that's going to be somewhat difficult to meet in terms of the corresponding displacement time history. So that's a particular challenge for this specification. So we're going to synthesize a series of wavelets as a base input time history in order to satisfy this SRS table. Now, there is not a unique time history which corresponds to this SRS. Rather, a given SRS can be satisfied with many different types of acceleration time histories. So our goals, of course, the first one is to satisfy the SRS specification with the least amount of error as reasonably possible. But also we want to minimize the displacement, velocity, and acceleration of the base input in order to stay well within the limitations of the shaker table. So here are the steps for our synthesis process, and these steps would make Rube Goldberg proud for those of you who know who Rube Goldberg is. Step number 1, generate a random amplitude, delay, and half sine number for each wavelet. Constrain the half sine number to be an odd integer greater than or equal to 3, and then these parameters will form the wavelet table. The frequencies will be at a predetermined step of 1/12 octave, or some other step according to our choice. Step number 2, synthesize an acceleration time history from the wavelet table, and that's rather straightforward using the equation that we saw several slides ago. Then we calculate the shock response spectrum of the synthesis for step number 3. Then for step number 4, compare the shock response spectrum of the synthesis to the specification. Then form a scale factor for each frequency based on the amplitude of the synthesized SRS and the amplitude of the SRS specification. We then scale the individual wavelet amplitudes in step 5. Step number 6, generate a revised acceleration time history, and that's based on the previous scaling. Step number 7, repeat steps 3 through 6 until the SRS error is minimized or an iteration limit is reached. Step number 8, calculate the final shock response spectrum error. Also calculate the peak acceleration values, integrate the signal to obtain velocity and then again to obtain displacement. Calculate the peak velocity and displacement values. Step number 9, repeat steps 1 through 8 many times. Step number 10, choose a waveform which gives the lowest combination of SRS error, acceleration, velocity, and displacement. And that will be by some weighting factors which we will discuss later on. So let's open up our MATLAB workspace. Then let's set up an SRS_spec array with the breakpoints from the Mill Standard 810E table, which was shown several slides ago. So the first frequency is 10 Hertz and then 9.4 G, then 80 Hertz and 75 G, then 2000 Hertz and 75 G. And this will be our input specification for an upcoming MATLAB script. Now we're still in our MATLAB workspace, and let's enter wavelet_synth, and this is our MATLAB script for wavelet synthesis. So this program synthesizes a time history using wavelets to satisfy a shock response spectrum, or SRS. The program also optimizes the time history to yield the lowest overall error, acceleration, velocity, and displacement. The optimization is performed via trial and error, and also there are some weighting factors which will be discussed later. So our data input method will be choice number 2, internal MATLAB array. The input array must have 2 columns, natural frequency in Hertz and the SRS in G. The array name which we set up previously and now we will enter is SRS_spec. Then let's choose 1/12 octave spacing, which is choice number 3. Our damping format will be Q, which is choice number 2, and we will have a Q value equal to 10, which is the typical value. The number of trials we will choose is 200, and this will work for our sample problem. If we were doing this in earnest, we might have maybe 1,000 or even 2,000 trials, particularly if we had a very difficult specification to meet in terms of acceleration, displacement, and the SRS error. Our units will be choice number 1, that will be G's, inches per second, and inches. Next we enter the displacement limit, and this will be in inches 0 to peak. And for this example, let's use 0.65 inches. Now most shaker tables should have additional margin beyond that, but we're giving ourselves a little bit of a safety factor. The sample rate will be 20,000 samples per second, and that's 10 times the highest SRS frequency, which was 2,000 Hertz. So 2,000 Hertz times 10 yields an equivalent sample rate of 20,000 samples per second. For our select condition, we're going to set the duration, and we're going to use a duration of 0.25 seconds. Now this will allow us to have 2.5 cycles at the lowest SRS frequency, which was 10 Hertz from our specification table. In this slide, we're going to select the weight numbers. Now these will be used to select the optimum waveform, and the suggestion is to use integers from 0 to 10, although these could also be real numbers and they could also be arbitrarily high. So the first parameter is the individual error, and this is the error at an individual frequency. So we want the worst case individual error to have a weight factor of 2. For the total error at all frequencies, we want a weight factor also of 2. For displacement, we want a weight factor of 1. For velocity, a weight of 1. And acceleration, a weight of 1. Now this is just for this example, and if you had your own problem, your own SRS specification, you might alter these values depending on the capabilities of your shaker with respect to the specification. And here are the results of our synthesis exercise. The peak acceleration is 25.274 g. The peak velocity is 39.119 inches per second. The peak displacement is 0.45 inches. The maximum error on a frequency basis is 2.013 dB. Now as you do this exercise yourself, your results will probably vary depending on the random number seed that the MATLAB script uses. Now for the output time histories, we have displacement, velocity, acceleration, and shock underscore response underscore spectrum. And those are internal MATLAB array names. There's also another array, and this is wavelet underscore table. And this has 5 columns: index, which is an integer, acceleration in g, frequency in hertz, number of half signs, and delay in seconds. So if you were to do a shaker table test using the synthesis, you would have 2 options depending on how your software is configured in your control computer. One would be to simply use the acceleration file and call that in as an ASCII text file into your vibration control computer. Or maybe your control computer can accept a wavelet table. Now if that's the case, you may have to vary the columns depending on the required input format for the control computer. And here is the resulting acceleration time history for our synthesis process. So this graph has a y-axis of acceleration in g and an x-axis of time in seconds. And this waveform in some sense is like a reverse sine sweep, where we start at a higher frequency and then we sweep down to a lower frequency. And that's a rough description. And here's the corresponding velocity time history. Now this is integrated from the acceleration time history. The y-axis is velocity in inches per second, and the x-axis is time in seconds. And note that the signal has a net value or ending value of 0, which is very important for shaker table testing. And here's the displacement time history as integrated from the velocity. The y-axis is displacement in inches, and the x-axis is time in seconds. And the final value of the displacement is 0. And again, that's very important for shaker table testing. Also note that we had specified in the MATLAB script that 0.65 inches was our maximum limit. But in this case, we've done better than that, and the peak absolute displacement is about 0.45 inches. So the signal appears to be a very good candidate for satisfying the shock response spectrum specification, and that will be shown in the next plot. And here's a shock response spectrum, and the x-axis is natural frequency in hertz. The y-axis is peak acceleration in g. Now, the specification is given by the black curve, which is in the middle of the three black curves, and this was from Mill Standard 810E. Then we've superimposed plus and minus 3 dB tolerance bands about the nominal specification. Then the blue curve is the positive shock response spectrum from our acceleration synthesis. The red curve is the negative shock response spectrum from our synthesis. And for both curves, we are reasonably within the plus and minus 3 dB tolerance limits. So it appears that our synthesized acceleration time history is good to go for a shaker table test. Now, if we wanted to achieve a time history with an even smaller amount of error as a safety margin, then we could go and synthesize some additional cases. But let's stick with this waveform for now. So we may have a need to save our wavelet table into an ASCII text format. And if you already know how to do this in MATLAB, or if you have some way of doing that already, that's fine. Please continue to use the method that you're accustomed to. As an alternative, I prepared a MATLAB script which will guide you through this process. So in this case, I type in data_convert. Then this program converts MATLAB data to ASCII text data. The output file name for this example will be wavelet_table.txt. Enter the MATLAB data format. This will be choice number 1, where the data is in a single array. Then enter the MATLAB vector or array name. In this case, it is wavelet_table. And then we use single precision, which is choice number 1. So this will save the wavelet table in ASCII text format on the hard drive. Then this wavelet table can be imported into the vibration control computer. Or we could use the same process for the acceleration time history and then convert that as an ASCII text file into the control computer. And that process will depend, of course, on what type of control computer is being used and what type of software options that it has. In this slide, we have a single degree of freedom system. This is a spring mass system that we've used several different times in previous units. So we have the mass m, the stiffness k from Hooke's law. We have a dash pot with coefficient c. Our base input is y double dot, and our response of our mass, the acceleration response, is x double dot. So let's take our acceleration file that we've synthesized and let's apply that as a base input to this system. And let's assume that our system is a circuit board with natural frequency of 400 Hz and a Q value equal to 10. And we'll be using MATLAB script arbit.m, which we've run before. So we are in our MATLAB workspace and we are running script arbit. So this program calculates the response of a single degree of freedom system to an arbitrary base input time history. So we need to have a file with 2 columns, time in seconds, and acceleration in g. In this case, let's choose option 2, which is a file preloaded into MATLAB. and the matrix name is acceleration. And this is our wavelet series that we synthesized several slides ago. The natural frequency of our circuit board is 400 Hz. The damping format is 2 for the Q value, and the Q value will be 10. For include residual, let's say 1 for yes, and this will allow the shock response spectrum to calculate a duration with one additional cycle beyond our synthesis. So the base input will be 0 beyond the synthesis, and the response of the spring mass system will simply be a free response or natural response based on the velocity and displacement as the synthesized pulse ended. And then for the results, the resulting acceleration response absolute peak value is 78.22 G. Now your absolute peak response number will vary depending on your base input and depending on the random number seed that MATLAB used as discussed earlier. This slide shows the acceleration response of the mass to the synthesized base input. The y-axis is acceleration in g, the x-axis is time in second. The peak absolute value reaches a level of 78 g, and beyond 0.25 seconds you can see the effect of the residual response, which appears to be simply equal to 0, so the residual response was not important for this case.